Welcome to Module 7, Statistical Analysis, Topic 7.4, Data Cleaning. By the end of Topic 4, participants will be able to dichotomize variables, create and use dummy variables, address missing data and understand imputation, conduct basic data wrangling steps such as merging and joining data, and perform these data cleaning steps in Stata. Please note that you can follow along with all commands in Stata syntax with the do file Module 7 Topic 7.4 example syntax and the 2017 mixed 10% random sample data file. We'll begin with dichotomizing variables. Dichotomizing a variable means to create a binary variable from a variable that has more than two categories or more than two numeric values. We discussed why we might want to create a version of a variable with less detail in Topic 7.3, and here we'll walk through how to do this in Stata. We will create a new variable using conditional statements. Here we have a statement that tells Stata to generate a new variable, or gen. We tell Stata to generate a variable, and we give variable a name, and then we tell Stata what that variable will be, meaning the equation or value of an existing variable that we want to use to create the new one. We use replace in order to assign additional values to our new variable. Let's look at an example from the mixed data in which we create a new variable that takes the value 1 when an infant is less than 1 year of age and 0 otherwise. First, we summarize the variable AN4, which is age of child in years, with detail to observe the central tendency and spread as we covered in Topic 7.3. We've already decided we want the split to be between 0 years of age and 1 or more years of age, so we don't have to make decisions based on the spread. But this helps us to check our work and see how the new variable will be distributed. We then use the command gen and our new variable name, age less than 1 year, which we set equal to 0. We then ask Stata to replace age less than 1 year with 0 if the value of AN4 is greater than or equal to 1, which means 1 year of age. Then we summarize our new variable with detail to assess the results. I always recommend checking any variable recoding or new variable creation by comparing frequency tables of the old and new variables, or by running a cross-tabulation of the two variables. This helps us see if the old values were correctly coded into the new values. We have frequency tables for AN4 and our new age less than 1 year variable on the left, and a crosstabs on the right, and we can see that the values seem to be recoded properly. You can also dichotomize by simply creating a new variable that you set equal to some condition of another variable. In this example, we generate a new variable with the gen command and call it age less than 1 year version 2, or age less than 1 year v2, and set it equal to AN4 less than 1 year of age. Then Stata creates this new variable with all observations of children less than 1 year of age with a value of 1, and then it defaults to assigning a value of 0 to the remaining observations. Be sure to be aware of missing data that might be transformed into your new value. We see that there are only 1,168 observations of AN4, but we are getting 1,181 observations of our new variable. So it is likely coding some children who do not have a value for age as a 0 for our new variables. We'll look at how to approach missing data later in this topic. When you want to create categories of a new variable from a continuous variable, the command cut is your friend. You can create cut points from the distribution of the variable from smallest to largest values. For example, we'll use the cut function to look at creating 4 categories of BMI for all children in the sample who have a BMI less than 30. First, we'll summarize BMI for those with BMI less than 30 so that we can see where the quartiles are in the distribution. We see that there are 1,157 observations of BMI less than 30. If you recall from 7.3, this summary detail gives us the smallest 4 values and the largest 4 values, and the values for each listed percentile. Here we see that our smallest value is 9.14, so our first quartile contains BMI from the smallest value of 9.14 to 14.25, which is the 25th percentile value. The next quartile is from 14.26 to 15.23, our 50th percentile value. The third percentile from 15.24 to our 75th percentile value of 16.40, and 16.41 to our largest value, 28.55, is our highest quartile. Now we can use these values to create cut points. We used the values we found for the quartile ranges to create the cut points at 9 for the lowest, then the upper limit of the first quartile, 14.25, then the upper limit for the second quartile, 15.23, and so on. When we run our command and then look at the table of our new variable, we can see that we did an excellent job of making roughly equivalent quartile categories for BMI. Similarly, we can use the recode function and command to recode BMI into categories. First, create a new variable so that you do not recode into the same variable and replace your original values. If you want to replace your original values, you don't need the new variable, but I would strongly suggest that you never recode into the same variable. Here, our new variable is called BMI underscore 4C for BMI 4 categories. Then you type the command recode, and here you can list the values that you want to go into the new categories. In this example, a / indicates a range of values. We're using the same range of values here as in the previous example. You can see in the output that when we cross-tab BMI and BMI 4 categories, we get the 4 categories of BMI as columns. And while I couldn't put the entire output here, the beginning and end show the values for BMI are properly coded. You can find additional syntax for recoding variables by searching recode through the help menu in Stata. But here, the basic syntax consists of recode and then the variable or list of variables to recode, and then a set of rules for recoding, examples of which are shown in the table. You can add generate new variable to the end to tell Stata to recode your variable into a new variable rather than creating the new variable first, as we did in the previous slide. We can add labels for our variables and values with the label function. To see a list of value labels for all of the variables in your data set, type label list. You should try this with the mixed sample and see how values are labeled. You can also type label list for one variable or a few. To define labels for a variable, for example, one named myLabel1, we can type the command label define and then the variable name, and then each value of that variable and the label you would like to attach to it in quotation marks. You can repeat this for all values you want to label. If you want to add additional labels later, you can simply do the same command with the word add at the end. Say we'd like to label our BMI categories as quartile 1, quartile 2, and so on. We can type label define, then our variable BMI underscore 4C, then the values and the labels. We can then type label list BMI underscore 4C to view our value labels. You can also search the label function in the help menu to find commands for labeling your new variables or recodes. Here's a list of commands you may find useful, but you can find more in the Stata help. You've seen how we create new variables with the gen, generate, and egen commands throughout this topic. This is just one example of how you can also create a variable by inputting a formula that transforms or uses other variables. In this example, we can use the actual formula for BMI of weight in kilograms divided by height in meters squared, because we have weight in kilograms in the mixed data, which is variable AN8, and length or height in centimeters, variable AN11, which we can convert to meters squared. We simply type the gen command with the name of our new variable, BMI underscore new, and then set it equal to the formula for BMI with our variables in place. Then we can summarize the data alongside the BMI variable in the mixed data to make sure that our formula was correct. We see from summary measures that it is the same. Sometimes in our data sets, we have values that we couldn't observe. These may be represented as empty cells, a period, or with unusually high values like 99.99 or 99999. You can use the describe function to see if you have missing data. Please use the MDESC function in Stata to find information about missing data if missing data is coded as a period. You may need to install the MDESC package in your version of Stata, which you can do by searching for it in the help menu and clicking install. When we perform MDESC, or it's short for missing describe, on the mixed data sample, we see that it will give us information on the number and proportion missing for each variable, given that those missing values were indicated by a period or an empty data cell. When we summarize BMI with detail, we see that the largest percentiles contain values of 99.99, which is odd because I doubt that there are actual children in the sample who have a BMI of 99.99. Sometimes you have to go back to documentation of the survey or data collection process and see what other potential entries or values for missing values may be used in each variable or data set. If we visit the documentation for the mixed data, or even just by looking at all of the variables in the label list, we see that there's a flag for errors in BMI reporting called BMI flag. If we type the command label list, we'll find a list of all labels for categorical variables in the data set, and we see that BMI flag value of 1 means that there's an error with that BMI. If we look at the table of BMI flag, we see there are 24 errors, and by creating a crosstab of BMI and BMI flag, we can see that all of the BMI values of 99 and greater are errors, and in fact, all of the values of BMI greater than 25.56 are flagged as errors. You can search for and install packages for the commands missing describe and MV patterns, or missing value patterns, in this data help menu. You can run either command for the entire data set or for a list of variables. mdescribe will tell you the number and percent of observations coded as missing with periods, as mentioned before. The command MV patterns will give you a list of each variable, variable type, number of observations, number of missing values, or MV, and the variable label for a list of variables that you provide or on the entire data set. It will show you patterns of missing values as well, with a plus sign indicating that the value is valid and a period indicating that it is missing. We see in this output that several variables had observations missing for 13 participants or rows. And when we look at the patterns, it appears that for 13 rows, data were completely missing, indicated by 5 periods. Sometimes it is okay to remove all the rows with missing data from our data set, and other times it is not. When we cannot remove all of the rows with missing data, we can use a multiple imputation approach to predict and impute values for our missing observations using what we know about the other variables and observations. In short, it uses modeling to predict what the value of the missing data would be, given all of the other data we have for that participant. This is beyond the scope of this specific training, but can be done in collaboration with a statistician or by searching the help menu for multiple imputation and following the instruction there. This takes time and thoughtfulness to complete. There's also a link to a useful document on multiple imputation in this slide. Sometimes we might need to join data sets or data matrices together. For instance, if we have collected data at different time periods or from different populations, or have it stored in separate places. Assuming two data sets or data matrices have observations or participants in the rows and variables in the columns, and that they have the same number of variables, we can concatenate, meaning to join or append, the two data sets by row using the command append using, and the file names or file paths to the two data sets. In this example, imagine we've created two different Stata data sets called Laos PDR Group 1 with 394 rows of observation and Laos PDR Group 2 with 393 rows of observation, and creating a variable called SVAR for shared variable, which had a value of 1 for group 1 and a value of 2 for group 2. Running the append using command with the file path to each dataset, and then running a table for the variable SVAR, tells us that the datasets were joined properly, as we can see that the frequency of SVAR 1 was 394 and SVAR 2 is 393, which are each the ends for each data group. In other cases, we may want to connect two datasets with the same sample or participants, but with different variables. Sometimes both datasets might have similar variables, but both must have at least one common variable with which the merge can be performed. We can do this with the merge function in Stata by typing the command merge 1 to 1, then the variable that the datasets share, and then using and the name of the dataset that we will merge with the current dataset we have open. In these example datasets, one is called subset 1 and contains the 4 variables UB9, CAGE, BMI, and sample ID. In subset 2, we have variables IM2, AN13D, BMI, and sample ID again. While they share BMI in common, we can't merge with BMI because values for BMI are not unique to each participant. Sample ID is a unique value for each participant or observation. With subset 1 open, we use the merge 1-to-1 command with sample ID using the file path to the subset 2 dataset. You can see that it gives us a result in which all of the 1,181 observations were successfully matched and 0 were not matched. We can use describe to see that all of our variables are in the new dataset with no duplicates. You may choose to practice these data management skills by repeating some of the commands we've introduced today on variables of interest in the Lao PDR Mix 2017 random 10% sample data. You can select at least 10 variables of interest, including both categorical and continuous data types, create dummy variables, examine missing data, split your dataset, and merge by row and by variables. In summary, you should now be able to use Stata commands gen, generate, replace, egen, cut, recode, and label to create, label, recode, and dichotomize variables. Identify missing values using the MDESC or missing describe and MV patterns or missing value patterns commands, and by using summarize and describe to examine data values that may seem out of the ordinary. Understand the basics of imputing missing values and know where to find more information. Install packages or functions in Stata, and combine datasets by row using the append function and by variable using merge 1-to-1 commands. Final thoughts. Data management is essential to conducting rigorous data analysis and having accurate results. It can be very easy to make and report incorrect conclusions because of small errors such as missing data or improper recodes. Invest the time in cleaning your data set well and recording all the steps you've taken, and you'll save future time, resources, and energy.